great pleasure for me to tell you something about our work on synthesis of nanoparticles and nanocomposites using the microwave plasma process. The first question that you may have is, why are plasma processes so special? In a plasma, the reactants are ionized, and therefore there is a higher probability for chemical reactions at lower temperatures. In a standard gas phase process, in general, we have reaction temperatures above, let me say, 1200 Kelvin, and in case of plasma processes, we can start chemical reactions roughly above 500 Kelvin. Are there special advantages in using microwaves? Yes, especially using microwaves, we can work under reduced gas pressure. This gives us the possibility of low reaction temperatures and therefore more flexibility in the selection of reaction conditions. Furthermore, I will tell you something about the design of the equipment for microwave plasma synthesis. And you will see this is a relatively cheap equipment, at least compared with conventional ones. And this equipment allows the synthesis of bare and coated particles. You see that the products have some special properties. I will tell you something about superparamagnetic or luminescent particles. And in addition, what's very important, particles combining properties which are in general incompatible. Looking at nanoparticle synthesis, we have in general a series of requirements. The first one, and most important, is that the chemical composition has to be reproducible. Special wishes are that the particle size is reproducible, and in addition, the particle size distribution should be very narrow. This is because many of the properties of nanoparticles are size dependent. And last but not least, we do need the possibility to have the possibility to produce coated particles, because this allows us the combination of properties. Now, looking at conventional gas phase processes, it's obvious we are applying neutral particles. And as I said just before, in most cases, the chemical reactions will start around 1200 Kelvin or so. In a microwave plasma process, we apply electrically charged particles. And it's very important to realize that the electrical charges of the particles have all of for the particles the same sign. Therefore, the particles are repelling each other. This limits particle agglomeration. Because of the ionization of the reactants, the application of microwave plasma makes low reaction temperature possible. And depending on the gas pressure and the microwave power in the system, the reaction temperatures may be adjusted in a range between 500 and 1200 Kelvin. To obtain appropriate results, the gas pressure is to be selected in a range between 1,000 and 10,000 Pascal. Now, for the microwave power supply, one may use the standard frequencies, 0.915 gigahertz for larger equipment, and 2.45 gigahertz, the so-called kitchen frequency for laboratory equipment. Now, what is so special with charged particles? We have to realize the capacitance of a sphere is directly proportional to diameter, and therefore the capacity is proportional to the diameter. Necessarily, in a closed system, all the particles carry the same electrical potential. Therefore, the electrical charge of a particle is well known, the product between electrical potential and the capacity. And as the capacity is proportional to the diameter, the electrical charge of the particles is directly proportional to the particle diameter. Now, the force acting between two charged particles is equal to the product of the electrical charges of the particle divided by the distance between the particles squared. Lastly, the force between two particles which are going to collide and agglomerate is proportional to the product of the diameter. And now this is important, as this force is repelling, because all the particles carry electrical charges with the same sign, the agglomeration of particles is limited. This limits the increase of the particle size during synthesis. Now, how are the particles set up? In the case of conventional gas phase processes, the probability the two particles are colliding and to form a larger one is proportional to the square root of the product of the diameters. In case of electrically charged particles, the things are a little bit more difficult. Certainly, we have the geometry-based probability, but we have to multiply it with the change of this probability due to the electrical charges, which is 1 over the product of the diameter. And therefore, this probability is inversely proportional to the square root of the product of the diameter. Now, let us look at this in case of neutral particles. The probability for particle growth increases with increasing particle diameter. And in case of electrically charged particles, the probability for particle growth decreases with increasing particle diameter. This limits the growth of the particles. One may use these results for modeling calculations, and this kind of simulation shows, for example, here on the left-hand side for neutral particles that after a certain number of reactions, when we collisions between particles. We have a very broad particle size distribution here. We have a maximum particle size of around 100 with an arbitrary units. And additionally, here we see a significant amount of unreacted material. In case of electrically charged particles, the things are different. We get a very narrow particle size distribution after the same number and after the same number of reactions. We mean of the same reaction time. Here we have a very narrow size distribution here. The maximum size is around 20, and the average size around 10. Here is the average size around 40. With neutral particles, we never ever will have the chance to get a narrow particle size distribution comparable with the case of electrically charged particles. Now, let us look at the starting material for the synthesis. We need a carrier gas, which also carries some of the reactants. To get oxide as carrier, we take argon or nitrogen and add some oxygen. A few percent in the gas is by far sufficient. To get nitrides, again, we use argon or nitrogen as carrier gas. And for the chemical reaction, for the formation of the nitride, we add ammonia. We can make many other compounds, for example, sulphides. In this case, one uses argon as carrier gas and hydrogen sulfide as reactant. For the metals, it is recommended to use as far as possible the chlorides because they are very simple to handle and in general quite cheap. In case we don't have sufficient carbonyls at hand, chlorides at hand, we can also use carbonyls, for example, iron carbonyl. For iron, also the chloride is possible. However, for gold, we don't have a useful chloride, and therefore we have to use the carbonyl or the carbonyl chloride. But for the selection of these starting materials, it is necessary to find compounds that evaporate at relatively low temperature to avoid sublimation. Additionally, we have to avoid sublimation at the cooler parts of the system before the reaction starts. As I said in the beginning, it's also possible to synthesize these ceramic particles and to coat them with a polymer, for example, PMMA. For PMMA coating, in most cases, methacrylic acid is very useful. One can also make coatings with fluorinated polymers, why not? Now, let us see how is the equipment set up. We have a generator for the microwaves connected with a waveguide to a resonant microwave cavity. Our reaction tube passes this resonant microwave cavity, and one end we introduce the carrier gas with the evaporated precursor, and on the other end we get the off gas and the product. What's important is that the microwave cavity is closed by a so-called cut-off tube to avoid leakage of the microwaves. To get coated particles, we just have to take the same system twice and to add the second precursor here in between. One can also make particles coated with a polymer. And first, we have the synthesis of the ceramic particle. And then we introduced an organic precursor, and in a conventional tubular furnace, we provided coating. And the polymerization occurs due to the temperature in this tubular furnace and or also under the influence of the UV radiation of the plasma. And in the end, again, we have the coated particles and the off gas. How the things look like. Here is a typical resonant microwave cavity. And what you see here are the tubes that helps us to avoid leaking of the microwaves. For experimental purposes, it may be of advantage to use a resonant cavity with variable lengths, but in most cases, one won't have too much advantage. How does a complete equipment look? What does a complete equipment look like? Here we have the synthesis of the core particles. Here is the coating step, and here is the collection of the product. This is a small equipment. Here one uses the so-called kitchen frequency is 2.45 gigahertz, and the power is significantly less than 1 kilowatt per unit. In most cases, let me say roughly 500 watt per reaction unit is sufficient. One can also make larger quantities with larger equipment. That's what you see here. Here you see a little bit larger reaction zones. The microwave frequency in this example was 0.915 gigahertz. These two boxes are automatic gravimetric support for the precursors. And this huge box here is the product collector. What does the product look like? Showing this, it is possible to compare it with so-called conventional products. Here we have a very conventional product, iron oxide. You see, is made by a gas phase, conventional gas phase process. Here we have a few large particles and many, many small ones. The diameter ratio between the larger particles and the smaller ones is about 10 or so. Diameter ratio of 10, that means a volume ratio with a factor of 1,000. This is remarkable, but there are many applications where this is no problem. For example, using as pigment in cosmetics. This here is a very special, highly specialized product. This is iron oxide with a unique particle diameter of 3 nanometers. This material here is used as a catalyst for burning processes. Now here, last but not least, we see a microwave plasma product. Comparing this here is the most important point. Nearly all the particles have more or less the same diameter. And this is important when we look at properties which depend on the particle diameter, like, for example, superparamagnetism. Now, until now, I told you a lot of positive things about plasma processes. However, you may also run into some problems. When we have a system, a conventional gas phase system without plasma, let me say we start with the chloride, we have the reaction with oxygen, and we get the oxide and some chlorine, and this reaction is in most cases above, let me say, 1200 Kelvin. In the plasma, our reactants are dissociated and ionized, and therefore this reaction will be at significantly lower temperature. Now, what happens in the case when we have a plasma and our carrier gas contains some water? In this case, at first, we have the same reaction as above. However, the water molecules are dissociated to protons and hydrogen ions. As our particles carry positive charges, and this OH ion, a negative one, they will react with each other and form a neutral particle. And as a result, the particles are not longer repelling each other. We get a broad particle size distribution. And that's what you see here. Here, on the left-hand side, you see the particles. All of them is more or less the same size. On the right-hand side, you see the particle size distribution in case that our carrier gas contained some water. You see, we have huge particles and a broad range of particle sizes. And here, nearly all the particles have the same size. One can also make, for example, sulphides. That's what you see here. Here, the lattice fringes are typical for the layer structure of the sulphides. Now, let's have a look at coated particles. This here is, for example, an iron oxide particle coated with zirconia. The lattice fringes that you see here show the crystallization of the zirconia coating. And here in the center, where the lattice fringes are nearly invisible, we have the iron oxide of the particles, and the lattice fringes are invisible because the lattice structure of the iron oxide disturbs the electron microscope. I've shown now a ceramic particle coated with a second ceramic material. Now, we also may have a ceramic particle coated with a polymer. That's what we see here. Now here, summarizing of the types of nanocomposite powder here. Ceramic core, in this case zirconia, coated with a second ceramic material, in this case alumina. The zirconia is crystallized. You see the lattice fringes and the alumina here on the outside is amorphous, is not crystalline. The second example is ceramic core coated with a polymer. This combination is very important, for example, for superparamagnetic material. And here, last but not least, a very interesting combination. Here we have a titanium core coated with platinum clusters. This combination that you see here is very important for catalytic purposes. Now, let's have a look at the properties of these materials, certainly of these composite materials. So, for example, superparamagnetism. Superparamagnetism is the property of isolated single ferromagnetic particles, provided they are sufficiently small. When we keep the particles on a certain distance, then we have the chance to have a three-dimensional body, which is superparamagnetic. And that's what we see here. We had gamma iron oxide coated with PMMA. As I said, superparamagnetism is characterized by no magnetic losses, no magnetic hysteresis. And you see here the magnetization curve of 300 Kelvin, of 200 Kelvin. There's no hysteresis. Only at low temperature, we have the hysteresis, in this case at 50 Kelvin. One can also prove that this is really so-called superparamagnetism by plotting the so-called temperature compensated magnetization curves. In this case, the magnetization curve, as you see it here, is temperature independent. This is a very sensitive proof of superparamagnetism. One can make magnetic particles. One can also coat the particles with a lumophore. In this case, for example, we had cores of iron oxide, hafnium, tungsten oxide, manganese oxide, and we coated it with anthracene, a very famous lumophore, and then PMMA. And here we see the fluorescence intensity. What's important and very interesting is that the fluorescence spectrum depends not only on the lumophore, but on the core oxide too. Now, we are able to produce superparamagnetic particles. We are able to produce luminescent particles. Why not combining these two properties? Then we have luminescent magnetic properties, a combination of properties which is not known in nature. Here you see on the left-hand side the magnetization curves. Here we use two different lumophores, the green line anthracene, the red line pyrene. And here on the right-hand side, we see the luminescent spectrum for anthracene and pyrene. This combination of properties is, for example, very important in medical diagnosis. One can also make very special properties, for example, superconductivity. Also, one can make zirconium nitride nanoparticles, polymer coatage, which shows superconductivity. Here, superconductivity is demonstrated by the magnetic susceptibility, because it is nearly impossible to measure electrical conductivity of isolated particles. Now, summarizing my presentation, I will conclude. The microwave plasma process is very useful for the synthesis of high-quality nanoparticles. The products show, and you have seen the electron micrographs, a very narrow particle size distribution, provided you keep all the rules that you need, that one needs. Furthermore, it is possible to produce coated particles, and the existence of coated particles allows us to produce material with a series of very special properties. Even a combination of contradictory properties is possible. And lastly, and this is for many university institutes very important, the equipment for synthesis is, compared to the conventional ones, very cheap. Yeah, and with this statement, I come to an end. I have to thank you very much for your attention. In case you have any questions, I will be happy to answer.